Okay, good. Are there any questions about Poincare duality? Have you tried to check it yourself?
Yeah, I personally don't have any question.
So, well, I just checked, and then indeed everything worked. So maybe no, I think I already deleted it. Well, maybe. Well, anyway, I just wrote it, and with my arbitrary sequence, just by definition, and then it's all fine. And I think, yeah, I think it was written here. Let's see, somewhere here. I think initially it was correct. So basically, when you, so here, for example, when you extend your form from U, the intersection of U and V, to U union V, so what you do, you just multiply it by the partition function, and it's well, it becomes different on U, different on V. Okay, so then on the intersections I agree, but if you want to consider what was the form on U, for example, you consider this one. Okay, this one. And if you want to consider on V, then you multiply by 1 minus rho V. And well, but since you want to check this kind of integration condition only like on any small compact sets, then it's fine. So it doesn't matter. So you can just check it for U, for V. And then it boils down just to switch off integration. So the order of integration. Okay, so if you try to do it and you fail, then just tell me and we can discuss at any time. Well, today I want to tell about Poincare dual of a closed oriented manifold, submanifold. So what is that? Well, usually if you have a manifold, well, that's manifold M, and then inside you have some submanifold S, then you have a homology theory. So you can define simplicial complexes and so on and so on. And then if you have a submanifold, it can be represented by a homology class. So for example, here you say that, well, there is a class of S in homology on M. So if you have the manifold of dimension K, then there will be a subclass. At least you can consider it. And so it's natural to ask, is it possible to do it in cohomology? Well, when you consider simplicial homologous cohomologies, you can do it by duality. But here we consider cohomologies as de Rham cohomologies. So we can try to understand it from the point of view of forms. Okay, so let's do it. So let's add Sk be a closed oriented submanifold of M. So M is also oriented and S is also oriented. And for now, we consider it's a closed subset. So it's not closed in the sense of closed without boundary and compact. It just closed in the topological sense, and not necessarily the compact set. Then here, just example, if you have R2 without 0, and you just take the spiral, like approaching 0, then it is a closed oriented submanifold, right? Because it's a closed subset, because we removed 0. So 0 is not here. But for example, if you do the same, but your spiral somehow approaches a circle like that, without actually converging to it, then it's not closed, because it's not closed in the topological sense. You take the sequence of points on your submanifold, and then the limit should be also inside your submanifold, but it's not there. Okay, so well, for such S, we want to consider the following thing. So we have an embedding. So it's a map from S to M. And let's define the Poincare dual of S. That will be a class in cohomology of degree n minus k. Okay, so we have manifold of dimension k, and there will be a class. And there will be some discussion about which form should I take to represent it. Okay, because, well, so you may have a class, but then it's always a question how to choose their representative. Okay, so how to do it? So if you have a form omega with a compact support in M, then you can integrate it over S. So how it looks like? Well, so somewhere here you have this form omega. It lives here, this support of omega. And then, okay, so what we do, we just, first of all, we restrict it to S. And then this support is closed because you intersected two closed sets, right? So you intersect the closed support of omega with closed S. So it's closed in M. Then it's a closed subset in M. And so it's a closed subset of a compact subset. So it's a compact in M. Since it's compact in M, then it's compact in S, right? Because the topology on S is just induced topology. Well, and so it means that if you want to integrate this omega over S, it's well defined. Okay, so it means that this omega the pullback of omega, so here it's omega, here it's pullback of omega. Here it will be in key form with compact support in S. And since your S has dimension k, it gives you a number. That's just a number. Okay, it's also actually we can track the sign, because if you have oriented manifold, so you've chosen some orientation and you have a form of the same dimension as the manifold, then when you integrate it, actually just the usual integral, like Lebesgue integral, but with a sign. Okay, so it means that for any form in omega k with compact support, we obtain just a number. And that we did by integration by S. Well, so it means that S induces a linear functional on this set of forms with compact support. And then from the Poincare duality, we know that this dual space is just the cohomology of degree n minus k. So it means that this integration over S corresponds to a unique class, which we denote by eta S in cohomology of M. This is up to now just a class. It's not yet like we don't know how to choose a representative of a form. But so here the notation suggests that there is some form eta S. Well, it exists, but we don't know it yet. Okay, so later we will have discussion about that. Are there any questions here? So you see here just a bit of topology, and then just the duality that we have from the Poincare duality. Okay, so the Poincare dual of S is this unique class, well, eta S, and the form is not unique. Okay. So here just another definition, if you wish, or just a property, that if you've chosen such a form eta S in this class, you can choose any form. Then you have the property that the integral over any omega which eta S, where omega is from case cohomology. Well, here it means that it just like that. Then the integral is equal to the integral of the pullback over S. That's equivalent definition. So you know that if such form omega S satisfies this property, then by Poincare duality, indeed it represents this class. Because actually exactly by this Poincare duality for the form of dual space. So if you know that it acts as a linear functional exactly as another form, that they must belong to the same cohomology class. Any questions here? Okay, can you hear me? Or maybe I'm disconnected.
Yes,
Yeah.
everything is clear.
We can.
Okay. Okay, good. Okay, so that was for the case when S is a closed submanifold, for example, this one. But now let's consider the case when S is compact submanifold. Well, then similar things can be done, but just a bit better, right? Because we have more restrictions for S, so we have less restrictions for forms. Okay, let's consider compact submanifold. It is also closed, right? Because well, it's a closed, well, it's compact subset of a Hausdorff space, so it must be closed. So it has this Poincare dual eta S, but it also has the so-called compact Poincare dual. So what is that? So again, so if we have S, we can integrate over it, and it gives a linear functional on the cohomology. Right? Before we had to take the compact cohomology, but now we can take just usual Durham cohomology of M, and if M is not compact, then it's something different. And so again, just by duality, there exists unique class, which is known by eta S prime, which now belongs to the cohomology with compact support. And that's all true if M has a good finite cover. So you remember we had some discussion then, well, the dual to cohomology with compact support, that's always a usual cohomology, but the dual to usual cohomology is not necessarily the cohomology with compact support, right? Because there are some problems. For example, if M is a disjoint union of infinite number of connected sets. For example, if M is just the disjoint union of like infinite number of sets, then the usual cohomology will be R in the power of Z, and the dual will be very big. But compact cohomology, they are small. So if you want to have this duality in both directions, so you need to say that, for example, M is compact, or for example, that M has a good finite cover. For example, if your M is just some union of Rn like that, then it also it also has such kind of dualism, even though if M is not compact. So compactness of M is not required, but we need to cover it by finite number of copies of Rn such that all the intersections also diffeomorphic to Rn. So let's assume that M has a good finite cover, and then we have such a unique class with cohomology with compact support, and well, with the same property that now if you take any form omega, you take its wedge with this form with compact support, then you integrate. That will be exactly the result of integration of the pullback of omega. Okay, and so this happens. This holds for any closed form omega, right? Because if omega represents some cohomology class, then well, we have such fact. But omega can be any closed form, because any closed form represents a certain cohomology class. Because sometimes, well, it's formulated in the sense of duality for cohomology, but here it's also kind of just a form, right? So you take any form actually, but the form must be closed. Yeah, because well, there's always this kind of not mistake, but some how to say some problems in notations, because people frequently denote the form and its cohomology class by the same letter, just to not to write a lot of parentheses. And here it's easy when you write this, have this definition. So we claim that it happens for any cohomology class omega which means that it happens, well, it holds for any closed form omega, because any closed form represents certain cohomology class. Yeah, okay. But the result does not depend on the concrete choice of form. Okay, so what we did, we constructed certain closed form. We can for any, so that's true for any omega, and since it's true for any closed form, then it's true for any closed form with a compact support, right? So it means that automatically the form omega s prime is also the just usual Poincare dual. Okay, so it means that if we have a compact Poincare dual, it is also the usual Poincare dual because it satisfies the same formula as a form, right? So for form omega, or for form eta, that's true. But maybe the class of eta will be different because compact cohomology and, well, usual cohomology, they may be different. So we will have examples about that. So we have a map. So from cohomology with compact support to the usual cohomology, and it sends this dual with compact support to just the dual. Okay, and so if S is a compact submanifold, then we can always demand that eta S, its Poincare dual, also has a compact support. So that's the moral of the story. Any questions?
I have a question about S. Can our submanifold has boundary?
No. So for us, all these things, they have no boundary.
And what the problem will be if S had boundary?
Well, if you have a boundary, then you need to define cohomology. So let's think. You don't have a Stokes theorem when you have a boundary. So it means that well, I mean, you can't do everything. You can consider forms on manifolds with boundary, but then, for example, you lose the duality. Because for duality, we use the covering by Rn. So, but you can have a theory of forms with boundaries. So you can also, for example, define the cohomology of interval with endpoints. And then I think when you speak about cohomology with compact support or cohomology without compact support, that becomes not very clear how to distinguish them and how to use them. Well, there are some, I mean, you can construct such a theory, but it just has a lot of, a bit more of notation. So, for example, as with usual homology, you can ask that, well, you have a manifold, you have a boundary, and you want to define a homology of the pair, right? So, for example, you want to consider forms which are zeros at the boundary. And then you have such something like sequence for a pair. So you can do it, but you can reprove all the theorems actually. So for example, what we've done before, we computed the compact cohomology and real cohomology of Rn. But here you will have to do it for for Rn -1 cross R bigger than 0. And the formulas will be different. And what else? Well, maybe homology will be the same. well, did I answer your question? Or you want to understand something concrete?
Yeah, no, just the general question. Thank you.
Yeah. One can do it, everything. So that's all possible, but then you have like twice more notation because then you have to consider not only cohomology of manifolds with boundary, but also cohomology of manifolds with respect to the boundary. And then you have some problem with compactness because sometimes your compact set hits the boundary, and then it causes certain problems. I don't remember which, but that's kind of bad. Where it's here, like that. And also you don't have a Stokes formula, so or maybe you have, but then you have this correction which comes from the boundary, and well, you need to take it into account. Yeah. Okay, so this can be done. I can give a link about that. So it's not more complicated than the usual the usual homology theory of manifolds with boundaries. But near the boundary, you have to do it like a bit more work. And yeah, and also maybe that was a question about the submanifolds with boundary, and then you have problems. Just imagine that you have here again you have R2 without a point, but then your submanifold is just interval. Then actually I think it's just the same as if you have your submanifold just a point, because when you perturb it and make it arbitrarily small, and then it means that, well, for such submanifold you don't have a duality. So because it's homotopy equivalent to a point. But for such big submanifolds like R embedded into R2, you have everything.
Okay, thank you.
Okay, good. Okay, now let's compute some examples with your help. So, okay, you have Rn. That's Rn. And you have a point P. Let's compute the Poincare dual of P. What should we do?
Okay, at first, P represents the zero homology class, yeah?
Who has zero homology class?
P. Point.
P. Point. Well, yeah, it's class homology. That's I don't know. So
in just on the present slide, we started with we had a submanifold S, and we choose the Poincare dual in the usual homology. So, no? We had some homology class of S.
So this about usual homology was just a motivation. Well, just wait a second. So just motivation, because formally we don't know what is homology. So that was motivation. So in how we defined here, we never used any homology. So you see, so instead of homology, we work always with cohomology or cohomology with compact support with duals. So we never have homology.
Okay.
Well, we probably should consider some zero-dimensional form and look how on the integral of this form over point.
Okay, what is zero-dimensional form? It's a function.
A function,
right? Okay, what should I do? I have a function.
I guess just evaluate it in the point P.
Okay, so point P gives me the map from C infinity Rn to R, and so what?
And we have to find a dual. No.
Okay, let's try to do it formally. So first of all, okay, we know what is our submanifold. Our submanifold is P, that's fine. But we also have dimension. What is dimension? Okay,
0.
0.
0. So where the dual class should belong to?
To the end of homology.
Hn of Rn. What is Hn of Rn? It's 0.
Yes.
So it means that here the Poincare dual of a point in Rn, basically just any form. So it means that we just need to take any, any form omega p, not omega, eta p, which satisfy this this quality. So it should be just any closed form. Is any closed n form. Just any. You see, so it's not, well, it's just trivial. Okay, but then let me ask another question. So now what is the compact Poincare dual of P? So what should we do? Well, let's try to recover all this procedure. So first of all, what to do if we try to first construct the usual Poincare dual? So here, to construct it initially, we considered certain forms degree k with compact support, right? And then we do something. And sure, clearly, since k is 0, so just functions. Well, and since we ask about homology, it should be locally constant functions. So it means that when we performed this procedure to construct the Poincare dual, we just taken the constant functions with compact support. So it was just only one function, 0. And because of that, we obtained nothing interesting. Okay, but if our manifold is compact here, so what should we do? So here, this our case with the point by integration over it. So we just evaluate at it. We have a linear function now on case homology of M. So what happens? So we have a function in our case, just function f in C infinity M, and indeed we just evaluated. Right? So it means that by duality, there should exist a unique class in the compact nth homology of Rn, which gives us this one. So what is that? So it means that we have any function, right? But here the function actually is not just any function. Here, hk of n. So in this case, it's just h0 of Rn. So just constant functions. So actually, it doesn't matter where we evaluate it. So actually, just the function f is just constant, and evaluation is just this constant. And then what we should find? We should find a unique class in nth cohomology such that the following is true. So we need to find a class in nth cohomology of Rn such that when you integrate it over Rn, you integrate constant times this, you obtain a constant. Right, and to do that, it's enough to take any form eta, just such that integral is 1 and with compact support. right? Just take any form like that, and it will be generator of the this cohomology group. And it provides us this duality. And then you see, then you have this, well, that was eta prime. And then indeed you have a map as above, so from eta prime, you have eta. Indeed, so here as eta prime, just a form which is closed, because any n form is closed with a compact support is integral 1. But then for eta s, for us, it's fine to take just any form, any closed n form, so just any form. So you see, so what's the difference? So sometimes this like cohomology with compact support, they may be not trivial, and this hn minus k of m is trivial. And in both spaces you have a dual form. Okay. Any questions? Everything's fine? Can you hear me?
Yeah, everything's
Yes.
fine.
Okay, good. So that was one example. So another example. Now let's do it in R2 without 0. So now I have a submanifold just the ray. So that's like this one. That's so since I don't have zeros, so that's just a submanifold, and it's closed, right? But not compact. But not compact. So it means that we can construct the usual Poincare dual, and I claim that it will be just the phi over pi, where phi is just phi rho is the polar coordinates. Right? So how to check it? Tell me. So now we have an answer, but we need to check that it's indeed the Poincare dual.
Well, we probably should check it by definition, like take any one the one form and integrate it over S, and then check that it is the same as integration.
Let's do it indeed. So we have the dimension is 1. So it means that in the definition, we should say that the integral over I upper star of any omega over S should be equal to integral over R2 without 0 of omega wedge d phi, d psi over 2 pi, where omega is any closed one form. Okay. Why is it true?
Maybe we can use a Stokes formula for the right integral.
Maybe, but how? Well, first of all, maybe I propose to write omega as a one form in polar coordinates, right? So, well, let's do it here. So omega is certain function f dr plus g d phi d theta, right? And so it means that well, when we integrate it here, so the part with d theta will die and will integrate only f. Also here you should take a form with compact support, right? So here it should be a form with compact support.
Well, the left-hand side will also be just integral of just f.
Why?
Because our s, it goes only like in the r direction.
Well, that's integral over f, but you see, so what's kind of the problem? Because here on the left, so when we find this integral, actually we restrict f only to the line x null, right? So somehow we need to explain why we don't care about values of f on the other plane, because f potentially depends on r and theta. How to find d omega? So because it must be a closed form. And then also how to compute.
Omega is just df over d theta minus dg over dr.
Well, I'm not so sure, because you see, when we do it in usual coordinates, that's true. But here we have polar coordinates. Maybe let's create one new sheet, because well, it's not much space. Okay, so again, so we have just this is 0, this is s. We want to show the integral over s over e upper star omega, and then just integral over r2 without 0 of omega which d theta over theta. Oh. Well, maybe we should do it like as omega, write it as a f x y dx plus g x y dy, and then it will be easy to integrate on the left, right? Because then here, when restricted to this line, this integral is just the integral from 0 to infinity of f of x 0, right? Because how you restrict it, you just say it, well, so here you have tangent vector, and you compute this form over this tangent vector. And when you can evaluate it, so here the tangent vector is d over dx. So this stuff, it survives, and dy dies. So maybe it's easy to explain what is d theta in usual coordinates. Do you remember what is d theta in usual coordinates?
I think it's x dy minus y dx over x squared plus y squared.
Mm-hmm. Okay, so and also we need the condition that the omega is 0. So what is this condition? It sounds like df dy minus dg dx equals to 0, right? Okay, so when we substitute this form here, we have the integral from r squared minus 0 of what? So here we have f x y x divided by x squared plus y squared mine plus g x y y dx dy. right? Well, it also divided by 2 pi. Okay, how to find this integral? Why it should be equal to, to this one? Any ideas?
Maybe the function like the form with the sum squares and the denominator is the just approximation unit, or how it's spelling.
No, maybe we just need to integrate over circles, right? So here we have the integral that we just care about the value f of x0, and here we integrate over R2 without 0. So maybe here we just need to prove that the integral over any such circle is just the value of f here. So it means that you fix x squared plus y squared to be equal to some constant, and then you integrate such a form. So basically here I wanted to integrate over d theta. So maybe see, what I want to say that the integral over a circle of radius r over omega wedge d theta over 2 pi, maybe it's equal to the omega at the point r0 evaluated at the vector d over dr. Well, divided by r. Right? Or we need to explicitly find this integral above. So whatever you prefer. How to find integral over a circle?
Use polar coordinates, no?
Yeah.
So we can rewrite this integral with the polar coordinates, remembering that the Jacobian of polar coordinates is on the plane is just r, yeah.
Mm-hmm.
So let's rewrite the upper integral over R2 without 0, like the integral with the change x's r cosine phi, for example.
Okay, so let's do it.
Y
So
is
x
r
is r
sine
cosine theta, y is r sine theta, and so it becomes integral of r square without 0 of f of r cosine r sine times r cosine plus g times r sine divided by r square 2 pi. And also we should multiply by r, right? Because the change of coordinates. And dr d theta. Okay.
But now we are integrating not over R2 without 0, I suppose. We have two
Yeah.
integrals, one
R,
from
yeah, S1 cross R
yeah,
bigger than 0.
yeah.
Yeah, and also here R squared disappear because here we have R square. So what happened if we integrate by phi? Well, it's difficult, right? Because here we need to integrate r f of this something times cosine plus g times sine divided by 2 pi. And also we have this strange condition about f at g, but in usual coordinates.
Oh, maybe it was better to use the Green's formula if we have this condition.
Well, maybe. How to use the Green's formula?
Okay, the Green's formula can say to us that oh no, no, I don't know what.
Well, something we have something from Green's formula. For example, that that's the integral over omega over any square is 0, right? So, for example, because of that, you can integrate omega over like any two circles, right? And to understand something about the difference. Well, how to find the integral of omega over any circle? Because so here, if we decided to integrate over theta, just to say that any such integral over with fixed r is just f of x0, well, we need to integrate omega over a circle. That's what we do here. Okay, so then, okay, so let's let the exercise. So actually, you just need to finish computations in either in Euclidean coordinates, either on polar coordinates. But to mix all of them, it's maybe the good idea from understanding point of view, but not good idea from the point of view of computation. I think you can just find this integral here just well by integration, right? So you have an integral over like over d theta of such thing, and you just need to compute fx minus gy. So what does it mean? Well, fy minus gx in polar coordinates, and that will give you a condition, and then you can compute this integral. Or you should just rewrite this well, okay. Okay, that was example that we need to do about finding Poincare dual. You see, even if you know that, if you know the answer, it's not obvious how to find it. But geometrically, it's kind of clear that well, what is a Poincare dual for a line? It means that if you have just on the picture, if you have any one form, you just integrate by over all such circles, and then that's dual to the ray. So, and this form, the theta over 2 pi, somehow it represents the circle here, right? Like any circle. right? Because if you just integrate this form, so it doesn't matter over which circle you integrated, you have the same answer. So for all circles, the integral of this form is just 1. Okay, so that represents the idea that any such circle intersects your array exactly once. But if you have some other curve, whatever, just any curve, then the number of intersections with this line is exactly the integral of d theta over this curve. Okay, so if you have like any curve here, like that, then its integral, the integral of the theta over 2 pi over such a curve, that's exactly number of turns around 0, which is the same as the number of intersections with array. So that's this homological perspective from intersection theory, if you wish, from usual homological homology. Okay, so that was one example. Another example, again, the same picture. Again, R2 without 0, but now we ask about circle. Just x squared plus y squared is 1. And since this is a compact submanifold, we can find both the closed Poincare dual and compact Poincare dual. Okay, let's try to do it now. So yeah, here we have a point, have here a circle, and that's my submanifold S1, so k equals to 1. And then I can associate to it both eta prime S1 and eta S1. So how to find it? What would you suggest? So we need to find some form such that integral over S1 over E upper star omega is equal to integral over R without 0 of omega which eta S prime, for example. How to do it? First of all, so here the dimension is 1. So what is H1 of R2 without 0, and what is H1 compact support H2 without 0? What are these?
First is R. Yeah.
Why? Okay, but what
Because okay, the R2 without 0 is homotopical equivalent to S1. S1. Yeah.
Okay. Okay. So
Isn't
then,
the generation is one form such that the integral by the S1 is 1? Yeah.
well, let's see. So here, just take any form, okay, alpha, let's say, choose here any form alpha, and you say that, well, it's enough to take any form alpha such that the integral over S1 would be just 1. And well, maybe also d alpha must be 0, right? Well, we know such form, such alpha is just d theta over 2 pi. Then we again have the same question. So is it true that, well, so here, so you propose it as what? As Poincare compact dual, compact Poincare dual, or as just Poincare dual? So here it's usual cohomology. So apparently you propose this one. So you say that, well, maybe this is equal to no, not to this one, to this one. So you say that maybe that's d theta over 2 pi. Well, how to check it? So first of all, indeed, that's form defined on the whole R2 without 0. So it's not with compact support. Its support is not compact. And you have that the integral over omega over S1, that's the integral over R square minus 0 omega, which d theta over 2 pi. So what do you think? Is it true or not? For example, if we take as omega just some form, I don't know, something like dr. Right, so if you take here as omega dr, for example, that on the right, the integral is definitely not 0 because we integrate dr wedge d theta. And here, if you take dr, well, surely this integral is 0 because when you restrict dr to any, well, tangent vector here, compute dr on any tangent vector here, it will be 0. So it means that no, this thing is not good.
Okay.
So maybe quite the opposite. Maybe it's better to take something like dr. So is it true that integral of omega wedge dr is equal to the integral over S1 of E upper star omega? Right, because this is so if you have such integral, so on the right, here only the part d theta survives from omega. Right, and then, well, indeed, if you have something like that, then you integrate d theta on the left, and then it's not 0. Because as in the previous example, so here you wanted to say that this like integral f x null here, that's the integral above, like in Fubini theory, that first integrated by circles, and then that's what we have. And here it should be quite the opposite. So here we should first integrate by the, let's say, these lines. And so this integral should be something like that. So we first integrate by dr, and the result will be just the omega computed at one point here. And also, apparently, this dr, it should have compact support, right? So if we consider just the usual Poincare dual, then we should integrate some forms with compact support. So we should multiply all them by something. Okay, anyway, so let me just puzzle you enough. So let's say that, so here you should also find both closed Poincare dual and compact Poincare dual in this example. And well, we discuss solutions next time. Discuss solutions next time. And if you will be able to present them, I will be very happy. Okay, so it's not me presenting them, but maybe you. Okay, but do you understand what to do? So basically, you just need to use kind of Fubini's theorem in both cases. But in one case, you should integrate first by circles. In another case, you should integrate first by rays. Again, maybe in polar coordinates. Because all this theorem, like all this Poincaré, construction of Poincaré dual looks like Fubini integration, right? So here you have integrals of forms of different degree. So on the right, so you have here two forms. On the left, you have one form. So how can you prove that the integral of one form is equal to the integral of two form? So, well, you use kind of Fubini's theorem. And also, it cannot be true for any form, because here you have to use that your forms are closed. Otherwise, it's not true. Okay, any questions here before we go to the next topic? Okay, no questions? Okay. Then, okay, so in general, Poincaré duality is an isomorphism between the RAM cohomology and the RAM cohomology with compact support. And so you can construct the dual homology theory. So the RAM homology with compact support is on the right here. It corresponds to usual so-called compact homology. That's, for example, for simplicial homology. As you remember, in simplicial homologies, you always consider kind of finite sums of simplices. So any chain in compact homology is always compact. But in closed homology, so there is also kind of theory to do that. So here you allow to use infinite summation in chains. And then, for example, so what would be the difference? For example, if you have in R2 without zero, so then the circle around zero is a homology class, right? Because it's not a boundary of anything. But in closed homology, the circle is a boundary. It's a boundary of what's here inside. Right? So that D S1 is a boundary of D. Because D actually is it's a closed chain. So it has infinite number of simplices. You can just have an infinite number of them, but it's closed. So its image is closed in the space that you consider. And so this will represent also this difference between the RAM cohomology and the RAM cohomology with compact support of R2 without zero. They just have different generators. Right? And usually people study only compact homology. So when in any course in homology, so you have this. And so that's usually is defined as HK of M, right? And then this HK of M it's H n minus k of compact support of M. No, here it's HK also. And then it's dual to Hn minus k of M. And that's the RAM cohomology. So the RAM cohomology, they are dual to the compact cohomology. So here you also can consider HK of M, usual one. It's the RAM. These are dual. These are equal. And these are equal. N minus k. Okay, so here, so from this perspective, it seems that there are simplicial homology, simplicial cohomology, and drum cohomology, and drum cohomology with compact support, but actually there are also closed homology and closed cohomology. But since they anyway are isomorphic to the drum cohomology, so people usually ignore them because, well,
I'm sorry. The compact homology is just isomorphic to singular homology with real coefficients, yeah?
yes. Yeah, singular cohomology. Or simplicial, well, it doesn't matter.
Or simplicial or cellular or other theory.
Yeah,
just
yeah,
okay.
so with any standard homology theory. But in any standard homology theory, you're allowed to take only finite sums of something, finite sums of cells, simplices, or whatever. But also there is a theory when you're allowed to take infinite sums only under the condition that the image, well, is closed. And then you also can do everything. But, well, actually, it makes not much sense. Because anyway, usually you need homology for many folds. And for them, it's maybe better to use just the rank homology. Well, anyways, they exist and they are not very interesting, at least that's how people think. Okay, so next thing is that the support of the compact Poincare dual of S may be shrunk to any open neighborhood of S. How can we prove it? So let's say we have S. Just take any neighborhood of S. So let's call it V. Well, and you remember that for S, you can construct this eta prime S in compact cohomology of V. Okay, and then it can be embedded to compact cohomology of M. And the integration, well, is usual. So for the integration, when you integrate over S, you don't care about where this S belongs to, whether it belongs to a neighborhood V or the whole M. So it doesn't matter. So for all the definitions and integrations. So it means that, well, that's the way how you find this support of omega S prime in a very small neighborhood. Just take a neighborhood, then inside this neighborhood, you still have the same Poincare duality and everything. So in this neighborhood, you find this eta prime S. So it means that this eta prime is a certain form which lives just in a small neighborhood of V. So we can choose it, right? Because this form eta S is a choice. So it's cohomology, well, its class in HK or HCK of M is fixed, right? But the representative can be chosen in different ways. And we can choose a representative very close to S. And then, so our next goal is to understand this representative better. Understand this representative better. So maybe write a formula for it. Okay, so for the formula, so once we solve the exercises above, so we will see that for a circle or for a line, it's easy to write a formula, right? But how to do it for a general submanifold? And actually, it means that we need to understand how to write this dual for S in the tubular neighborhood of S, right? And now, so we go to the vector bundles because, well, what is the idea is that the tubular neighborhood of a manifold is actually the vector bundle over it. And so if we understand how to write this dual form for vector bundle, then we understand how to do it for NES. Is it clear the idea?
Yes.
Okay, so now let's go to this discussion of what is vector boundness, and so on. So let me give you all the definitions, because at least half of the people wrote that, well, they don't know what is that. So let's do it this way. So let's say we have a manifold. That's M. And N is a manifold. And then we cover it by certain charts. So there's charts U alpha. And M is covered by U alpha. And now imagine that you have certain big space E, which is somewhere here, and there is a map pi from E to M, such that any preimage pi minus 1 of U alpha is actually U alpha cross Rn. Okay, so let's suppose this. And also suppose that the map from how to write it. So let's do it this way. So we have a map from so if you have two maps, U alpha and U beta, here U alpha and U beta, so they have intersection. That's U alpha intersect U beta. And then you have two preimages. So you have one preimage inside this U alpha cross Rn, and you have another preimage here. Yeah, it's U beta times Rn. And you want to say that this change of coordinates inside E, it's linear. So how to say it? So we just say that there are maps. How to define it? How to denote it? Okay, so so here, let's say that here these maps we call them phi alpha. So here it's phi alpha. It's a map to here. It's isomorphism, or homeomorphism. And then now we want to say that the map from the intersection, well, E minus 1 O alpha cross U beta. So it has under the image of phi alpha, it goes to U alpha cross U beta cross Rn. And under the phi beta, it goes to the same. But this map may be different. And so we want to say well, that both of them are homomorphisms. We want to say that the map, let's say, phi beta composition phi alpha minus 1, okay? That will be a map from U alpha cross U beta cross Rn to itself. Should be, well is linear in each fiber. Then E P M is called a vector bundle over M. So it is the idea that over each point of M, there is this copy of Rn, which means that, well, locally, that for any point there is small neighborhood, such that the preimage of this neighborhood is just this neighborhood times Rn. But that's not all. We also require that when we change the coordinates, when you go from one chart to another, this map is linear in each fiber. And then this map is called a vector bundle. So, and what does it mean linear on each fiber? Actually, here it means that there is a map which we denote by, let's say, G alpha beta. This will be just a map from U alpha U beta times G L and R. Right? So that's exactly what happens here, because here for every point we must show the linear map from Rn to Rn. So it means that for any point of the intersection, there is a map from, well, it's a linear maps from Rn to Rn. And so it means that we can determine a vector bundle by a covering U alpha of M and so-called transition maps. A transition map is just for any two indices, alpha and beta. We have a map G alpha beta, which goes from the intersection to G, L, and R, and should be, well, continuous, smooth, or smooth, etc. So it depends on the category where we live. So if you want to speak about smooth manifolds, then you want that such map is smooth, because we know what is this smooth map from intersection of two charts to G, L, and R. Okay, so, but also it's not arbitrary maps, right? Because we need that actually it's true that if you have the triple intersection, then G alpha beta composition G gamma G beta gamma must be equal G alpha gamma. Right? Because if we change coordinates when we pass from the map from the chart alpha to chart beta, and then change the coordinate to pass to the chart gamma from the chart beta, it should be the same as we just from the very beginning change the coordinates from the chart alpha to the chart gamma. Okay, so a vector bundle is defined above, so just a map with such properties that the preimage of every point is Rn, and when we change coordinates, the gluing is linear, but equivalently, a vector bundle is just a covering of M by charts, such that with transition maps given by such maps, such that you have this condition of compatibility. And then, so how you define the vector bundle using this data? Well, just for every U alpha, you consider U alpha cross Rn, and then you glue these U copies U alpha cross Rn using these gluing maps, transition maps. So, for example, you have a circle and you can have a like Möbius band on it. That will be a vector bundle. Any questions so far? So, for
No
example,
questions.
if you study the tangent bundle, so when you define it, you also show that for every point there is a neighborhood, such that the tangent bundle of this neighborhood is this one, and then when you consider the transition functions, they are given just by Jacobian, right? So you just explicitly show how you change the tangent vectors when you change the coordinates. What is maybe interesting here also is that so we can look at the group generated by all images of G alpha beta, right? So this group may be the whole G LNR, maybe not. So for example, if G alpha beta belongs to O n, so or to some other group, G alpha beta belongs to G. So then we call it G the structure group of the bundle. So it means that, well, sometimes if you just consider the if you just consider a vector bundle, you can ask whether I can change the structure group. So for example, my structure group now is G and R, so the whole group, but maybe if I just choose charts in a bit different way and this isomorphisms a bit differently, so that's phi alpha, phi beta, maybe after that my structure group will be smaller, and then smaller, 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 and smaller, because for example, if your structure group is just Z2, so then what happens? It means that you always glue these fibers like identically or just by multiplication by -1. So it means that your bundles very simple. So it's good to reduce the structure group of the bundle to a potentially smaller group. And for example, if M and E are oriented, then the structure group can be reduced to ON. So maybe it's true for non-orientable M and E, but I'm not sure. So how we prove it? So basically, first of all, we need to find some metric on the on the bundle, which is linear in every fiber. And then you do orthogonalization, right? Because then if you just manage to choose basis in every point, such that this basis changes smoothly when you go from one point to another point, then you can ask that when you glue this maps here, the base goes to the basis. So you can ask you can ask this maps G alpha beta to preserve the metric on fibers. Right, because for example, if you already have this metric, so you define it, then naturally when you use this map, G alpha, well, phi beta composition phi alpha -1, so it sends fiber to itself and it preserves the metric. And so this map automatically belongs to ON. Okay, so how to do it? So, well, as I said, to do that, you just need in every fiber here, so it's called fibers. P -1 of X is called a fiber for X. So that's my X. Here is copy of Rn over it, that's called a fiber. So in each fiber, I've chosen metric. And then, so when I glue this fibers using these maps above, it will preserve the metric. And so automatically my maps here will be to ON, because ON is exactly the linear maps which preserve the metric on the space. Okay, what else I wanted to tell you about vector bundles? Well, maybe, well, that was a short introduction as possible. Okay, so then the next time we construct the Tom class. So basically you construct the Tom class by integrations over the fibers. So here with small forms living here on these fibers of the tubular neighborhood of a manifold. Also, next time we discuss the exercises. Okay. Any questions?
Well, yes. How to define the equivalence of two vector bundles?
How to define what?
The
I cannot hear you.
equivalence. I mean, how to define the equivalence of two vector
Okay.
bundles?
Well, so it means that if you have a one vector bundle, you have another one, you have a continuous map here, which preserves the fibers. Here F preserves the fibers and linear on each fiber. Well, and it's commutative. So it means that, well, so for every x in M, F sends p minus 1 of x to p2 minus 1 of x, and it's a linear map. So that's how it defines the maps between between vector bundles, and if this F is diffeomorphism, so that's, well, F just a map. So that's definition. That's F is a map between vector bundles, and if F is diffeomorphism, then it's called well, these bundles are equivalent. Actually, you can check it also in terms of these transition maps, but it's a bit more complicated. So what you say that no, I think when we discuss the Czech homology, we can discuss it again. Let me write it here in Czech homology. And discuss again. So here it means that actually when you define this transition maps, it also looks like a cohomology theory, and this collection with maps looks like a cochain. So, and then so this equivalence relation will be just adding a cocycle, adding a co-boundary. So actually later it would mean that if you have this class the same for two vector bundles, then this will be the same. Well, this will be the equivalent vector bundles, but this will be later. Okay. But you can try to imagine what happens actually, because just imagine that you have here small neighborhood on your manifold, and here you just changed this identification above. So it will affect. So well, just take one of the covering elements here and change here the identification by alpha. So it affects this G alpha beta, right, in a quite simple way. So you just multiply them by this change of coordinates. And if you have two equivalent, if you have a vector bundle and another one who are equivalent, then you can choose a very small covering such that by such elementary moves, you can come from one vector bundle to another one, just to see how this transition function changes. change. Is it okay?
Yes, yes, sure.
Okay, good. Okay, then I stop recording.